the title of my talk nowadays is "There's no time for science as usual," and there is a reason. There is no vaccine for climate change. Okay, if you look at the CO2 emissions and what we need to do to actually just be at 1.5 Celsius, we will need to actually halve it during the next decade. We're already during that decade, and nothing is really being done. And of course, we have governments to blame, but we also have scientists. We need to actually accelerate our discovery process. So I'm writing a paper with my colleague Ted Sargent when we're thinking about what will it take to develop a material in about a year, right? So why develop and scale? Because if you think about it, the COVID vaccine was developed and scaled in a year. Okay, you can imagine that they have an infrastructure already built in Moderna and of course in the German BioNTech. But we also can build such an infrastructure, and even with that infrastructure, I bet you we could not come up with a material to filter water or capture CO2 or catalyze better ammonia production, etc., in a year. Okay, and that basically speaks badly for us, the chemists, the material scientists, the physicists, and the chemical engineers. If you really think about it also, for example, the biologists were able to lower the cost of sequencing a human genome over 15 years from $100 million to less than $1,000. That's way beyond Moore's law, way beyond exponential doubling every year and a half, okay? That was done because the biologists have already embraced automation, artificial intelligence, data science, way before us. So my thesis is that if we really think about the discovery process, truly involving AI and automation, but also thinking all the way to the end, all the way to manufacturing, then we might be able to have a chance to lower the development cost of a material, hopefully to 1 year and $1 million rather than 10 years and $10 million, or even 25 years, which is a traditional time scale. Can even more? Could we do it another time? If we do it another time, then we'll be in a new era, the era of materials on demand, okay? So that's a challenge that I've been trying to solve recently. And this is an example of me putting down my own research. Mike Assis, Roy Gordon, and myself in 2014 introduced a new material class. It's called organic flow batteries, okay? These are batteries made of organic molecules, redox molecules, okay? So it's a big field now. And it turns out that it took us 5 years and $1 million to get to one of the two candidates for the one of the size of the battery. Partly because it took us too long to actually follow this traditional design process. And I was a theoretical guy doing high throughput screening and calculations, but if you only make and test molecules at a time, you really don't move the needle. I argue that in the 21st century, it is not even an option that we continue doing science at the speed that we're doing. We have to change the way we do it. And if you want to think about that, then you have to break the silos. And as I'll show you in my talk, me as a computational trained physical chemist, I'm thinking about organic chemistry, I'm thinking about engineering, I'm thinking about computer science, etc. So you need to break the silos, bring people that is multidisciplinary together and solve the problem, right? If you want to save the planet, obviously there is a role for basic research as well. I mean, I'm not trying to teach basic research as well, but I like to do both. And in particular here then, what I like to call a self-driving lab, or a lab that closes the loop, is a lab that as a particular experimental data point comes in. It could be serial experimentation, it could be parallel experimentation, etc. The data is used to update the model about your experiment and then continue iterating, okay? So with this type of vision and work, then comes recognition, but also pressure. So this is 10 breakthrough technologies 2020 by an MIT Technology Review. AI discovered molecules. I co-founded the company Kevotics. I'm University of Toronto. I'm at Vector Institute. And I wrote a paper with Silicon Medicine. So even though this is not given to a person, I feel partially responsible for this. But also then I'm also partially responsible for this, okay? So there is a lot of pressure for us to really deliver AI discovered molecules. So when I say AI, we have to really think about what I mean by that, because AI now is so hot. But AI is a field as large as physics, chemistry, or material science, right? What do you mean by AI? Well, of course, general AI is a Terminator. I think we'll end this talk talking about the Terminator. But at the same time, I like to talk a lot about androids in my talk, so we'll keep talking about androids. But we're really talking about is shallow artificial intelligence, in particular machine learning, in particular deep learning and Bayesian modeling are the tools I'm going to tell you about today. but also are very interested in robotic process automation, as I've been telling you. So there are many other areas in AI that chemistry will benefit from. I argue natural language processing is going to be very huge. All of these areas need to be taken care of. So what is the difference, right, between the famous SAR that all our biophysicists and chemists and everybody has looked at? After all, we've done many models where we correlate electronic structure of molecules or orbitals or coefficients, etc., with a property, basically using usually a generalized linear model. We use a vector x prime, usually multiplied by a weight matrix that we fit and a shift that we fit, passed by a nonlinear filter f, and then we end up with a prediction. Okay, this is what people have done since the 80s, 90s, etc. It's nothing new. The difference between that and deep learning is that if you have more data, you can take that particular original feature that is the molecule graph where you extracted your descriptors, but you have enough data to generate your own descriptors on the fly, and they're optimized to the problem at hand. This is what I'm going to call the Z vector or latent space vector, that in the last layer of the neural network, we actually fed to exactly the same mathematical model. So you can always compare your traditional SAR with a neural network by just taking the last layer of a neural network and fitting, if you have the same number of parameters, and then you just going and see how well it does in prediction, right? So that's just kind of like to tell you that there's nothing new under the sun except the fact that we're learning a better representation of the features of our problem. We're learning to generalize better. Okay. So this is where my journey started. This paper in the journal Neurips, at the time was called NIPS, 2015. Collaboration with David Dubenot, now my collaborator, University of Toronto, Ryan Adams. They asked us, what do you use to design materials? I said, at the time, we were using these binary bit vectors. They were called the Morgan singular fingerprints from the pharma industry. They're a fixed length vector that actually hashes features from atomic, bond, next nearest bond, next nearest bond, etc., into a bit vector that then is hashed with the next bit vector, and bits are turned on as the features create this kind of like, beautiful turn on and off kind of pattern for a molecule. It's almost like a keyword code for a molecule, okay? A hash. So let me close my door because there's some noise here, sorry. So what David did that I think is brilliant, he said, well, look, I want to modernize this. I want to make it like a neural network. And I see people here that do quantum chemistry or quantum dynamics, like, for example, Len Sederbaum. Of course, many people in this room think that way. Of course, we, the quantum chemists, love derivatives, right? I mean, derivatives are everything. We calculate derivatives to move things in potential energy surfaces. We calculate derivatives to see non-adiabatic terms, etc., right? Well, what the machine learning people do that is amazing, right, is they have code that automatically computes its own derivatives, right? This is auto-differentiation. It's just amazing. So what you do here is you build this graph that contains the same hashing, but now with real valued numbers, hidden weight matrices W, and then back propagate or differentiate using the chain rule to optimize the parameters with the gradients. That's how neural networks are trained. So in other words, this is a graph neural network, okay, or convolutional graph network, that at the end of the day gives you a vector, but of real valued F numbers. Pretty much built cloning the circular fingerprint, but modernizing it. In Morse, we have more parameters, as neural networks do, but the super advantage of this, okay, the super advantage of this is that now we can optimize it to the problem at hand, and second, again, it's differentiable. So the most important thing I'm going to say is if you want to do machine learning for chemistry, molecular dynamics, photophysics, your favorite problem, number one issue is the representation. What is the representation that contains the most physics? What is the representation that is more relevant to your problem? There are some problems where bag of bonds is enough. Organic chemistry, sometimes you only think you need to know what are the functional groups. There are other problems where you really care about the spatial nature of the wave function to a lot of detail. Ultimately, you go to the electron density, properties, transition dipoles, etc., in real space grids. Or strings, I'll tell you a lot about strings today, but also graphs, as I've been telling you. So this is the Coulomb matrix, famously developed by, for example, Anatole von Lilienfeld. So all of these different methodologies will depend on what you want to do. And sometimes even a mixture of them is what matters, right? But let me tell you an example how the representation is everything. So again, a very elegant thing, like if you're a quantum chemist or a theoretician, right, you say, well, if this thing is a matrix vector product thing, what happens if I tensorize it, but also extract the symmetries, okay? So I want to figure out what are all the symmetries of the graph to actually lower the dimensionality of the problem. You know, like in physics, if you have some translational symmetry, you have to respect it. So in this case, all the graph symmetries were extracted and you projected out with this tensorial representation, this beautiful paper by Ray Condor, a mathematician. And you can see here how the RMSE and MAE for this particular data set, the Harvard Clean Energy Project, here we're trying to predict the power conversion efficiency of an organic solar cell based on its molecular two-dimensional graph. What matters here is that it's a two-dimensional, graph representation. And you can see how these very simple models, like the models that you got before, like SAR type models, saturate the same way as our neural graph fingerprint. Our neural graph fingerprint does as well or as badly as all the other models. But when you actually extract the symmetries, you actually have a qualitatively different result. This basically tells you that, again, you have to really think about your representation. Having said so, I have a very kind of bold statement. I don't work on force fields. I don't work like this beautiful work, a lot of it coming out of Germany as well, Beller, etc., where people are really thinking about how to build potential energy surfaces with machine learning. These are obviously advantages of it because the functional form is not a fixed force field form. It's actually a form that is learned by the nonlinear parameters of the neural network. That means that my friend Adrian Reuterberg and Ole Sisayev have a reactive force field that actually can do nanoparticles, right? Or they have protonable and deprotonable proteins. I argue that this particular technology is going to be replacing force fields for all intents and purposes. Like, why would you use a force field? If you can do 2 years old paper by Adrian, already has the same accuracy as MP2. Okay, it's about 10 times lower. Okay, and it can break bonds. So I'm not going to tell you more about it, but of course, this is 2 years old. Only prop actually, which is now in Göttingen, Germany. So because we wanted to follow up this field, like we're not experts in force fields, and it's really amazing, this field. Okay, so but now let's talk about photophysics. Let's tell you about. We also think about designing materials in my lab, right? So what materials do we design? So let's talk a little bit about the photophysics. So I am very interested in light-emitting molecules, organic photovoltaics as light absorbing, but light-emitting organic.
Sorry, Alan, you're muted. Maybe I
had no idea how I was muted. This is the first time this happens. It's almost like a Russian spy muted me. I was just giving my talk, so I don't know what happened. But anyway, I'm happy that I am able to speak again. So as I was saying, in my lab, I design organic photovoltaics and organic lasers, okay? So just to remind you a little bit about organic photophysics, you have a triplet. It's called the triplet because there's 3 excited states, right? That's where usually they generate. They can be, the degeneracy can be broken by a magnetic field, and that's the whole idea of a triplet. When you have an incoherent mixture of excitons coming in to emit light, you will have 3 lower single triplet and 25% of your excitations landing in the singlet, which means that the maximum external quantum efficiency of a traditional regular organic emitter will be 25%. But if you have a cell phone, you don't want to waste 75% of your light, of your electricity in non-radiative decay. So what people do is introduce transition metals to actually mix by relativistic effects the singlet and the triplet and get phosphorescence. Now, the problem with that is that then the molecule with transition metals cannot withstand the blue emission excitation energy. There's too many destruction pathways. The molecule basically blasts away if it's a blue emitter, right? The gap is too large. There's a lot of energy, and then you just break off the molecule. So the beautiful, beautiful work of Chihaya Adachi around 2012, he found the families of molecules that have a triplet very well quasi-resonant with a singlet, obviously below. We'll come back to this at the end of the talk. But if you have this triplet below the singlet, right, at that KT type of energy, then you can have reversing the system crossing and then fluorescence. That's called temperature-assisted delayed fluorescence. So back in 2014, we built the first machine learning workflow in my lab where we took 1 million molecules in a library, calculated about 100,000, used one of these convolutional neural networks to predict the million molecules, and then from there down selected 1,000, synthesized 40 devices. We got 3 champion OLED emitters, and we published in Nature Materials. Hey, feels good. Rafa became a professor at MIT. We were very happy, right? This is a typical professor thing, right? Well, I'm not happy. Why? I calculated 1 million molecules. I only made 40 devices. These 3 devices are not in your cell phone. They are enough for a paper, but they are not in your cell phone, which means I did not deploy the technology, which means I'm an academic publishing my Nature Materials, feeling very happy about it. You pat me in the back, reviewers. I pat you in the back. We do not move the scientific needle, right? This didn't really accelerate discovery. This is the paper that got me into robotics. I said, if I don't make my molecules, I don't accelerate the throughput here, I'm going to spend the rest of my career predicting materials that take too long to exist, right? So this is the moment to talk about Blade Runner. I see the gallery. How many of you have seen the movie Blade Runner? Raise your hand in the gallery. Okay, Manuel has seen it, Maximilian, Yannick, Ghana, Jonathan, etc. Excellent. You guys are still awake. I love it. Okay, so this is that elegant and beautiful man, Harrison Ford. Okay, so here you see Harrison. He is Deckard, and he is a Blade Runner. His job is to identify and kill androids. Hey, what happened? His job is to identify and kill androids. Here are the data points. Basically means that Batty, Sebastian, Rachel, Priest are actually his data points, and he has to classify them. And this is the answer. If you haven't watched the movie, I'm telling you the plot. So he has to kill these 3, and maybe he doesn't kill some of them. And the ultimate philosophical question is he himself an android or a human, right? That's the beauty about this movie. Now, this is the typical machine learning problem of classification and regression, android or human. Good emitter, bad emitter. I've been telling you about it the whole time, right? I emit a molecule, whatever. I am more interested in the second problem, the problem of Batty. Batty has to generate human behavior, right? He has to pretend to be a human to survive, right? He has a famous line about, I saw the moons, and and then he dies, right? He gets detected. He fails at generating human behavior. It's pretty tough. That is what is called a generative model. And now I want to ask you guys to raise your hand if you have seen these computer-generated faces, right? You probably have seen them on the internet, right? Some of them are pretty convincing, like this one. Convinces me. Some of them have some issues, right? You can see some defects on the generated image, but they still look like samples from the probability distribution. As a matter of fact, raise your hand if you have done Monte Carlo models or molecular dynamics as a homework or as an exercise for the reader, okay? Well, Rishi, Kai, all of you guys are doing Monte Carlo methods. Well, guess what? You have done a generative model. You have generated samples from the probability distribution of the Boltzmann distribution, right? Or, that's what you do also with molecular dynamics. So we make a living generating samples, right? That's what we do, many of us. So now, what the machine learning people do that is amazing is they learn the distribution of something that is not that obvious, okay? For example, the distribution of pictures of cats, right? So how do you do that, right? So this is perhaps my favorite paper of my career. I published tons of papers, right? Whatever. My group is large, published many things. This is one of my favorite papers. Besides my quantum computing work that I really like, this one, we did something really cool. So we took 250,000 drug-like molecules, and we ran it by what I consider one of the most elegant machine learning models of all time. It's called the Autoencoder. It has beautiful connections to information theory, to compression theory, channel theory, Shannon capacities, entropy, etc. Why I'm telling you all of that? Because for quantum computing, when I built the first quantum autoencoder in my lab, we had to learn the theory behind them. So what is an autoencoder? You can think about it as a communication problem. I want to send you some information, but I only have a certain channel capacity. So I will compress the information with a neural network, and I will decompress it back with a neural network, okay? And this particular information is a molecule. And I write it as a string, but I can write it as a graph, I can write it as a wave function, I can write it as whatever I want, okay? But what is really cool is that we compress information and then decompress information. And if we do not have any losses, and actually there are theorems, like the Schumacher compression theorem for quantum mechanics, for example, that tell you how much can you compress before you lose information. It has to do actually with in the quantum mechanical case, for example, with the number of non-zero elements of the trace of the, how big is the matrix, the density matrix of the diagonal density matrix of a quantum system. Right? In classical mechanics, it's the same thing. It's the Neumann entropy of the system, right? So you can compress up to a certain amount, but it's super cool because I can take 250,000 molecules, and turns out without, with machine learning, I can pretty much losslessly compress them, say, to 200 dimensions. Okay, that means that chemical space is about 200 dimensions, but it's actually differentiable space. So you go from a discrete point to a continuous point to a discrete point. So what we did that was new at the time is correlated that 200-dimensional space to a property, okay? And therefore, we can actually use a small model like a Gaussian process, or it can be any type of regression model you want, with that 200-dimensional space to climb property or properties, go back and project, and then because you have the decoder, you can decode and find out which molecule corresponded to your maxima. This is a so-called inverse design problem, the problem that I've been telling you about. I want to find a new material for water filtration, a new material for OLED, a new material for drug discovery. And therefore, this inverse design problem is very powerful, right? So anyway, there are many, many, many ways. I just told you the Monte Carlo is one example. There are many, many ways to generate samples from a PDF, okay? Here are some of the machine learning algorithms for that, okay? So I'll be telling you about the autoencoders in this talk, but I also was the pioneer of GANs for chemistry. And I'll tell you some results about GANs, but I'm not going to tell you how they work. So the reason I think this was awarded because in silico was mentioned is because I collaborated with in silico, Alex Voronkov, kind of as a consultant, okay? They set up an adversarial autoencoder, like the ones we like to think about, together with a bunch of molecular filters. And in 46 days, the random experiment where actually we tested all the way to rats. And we found very good inhibitors for DDR1 kinases. Obviously, a kinase is a very basic problem in drug discovery. Second, there's a lot of filters that filter the crap that is generated by these models. We worked with Wuxi that has a lot of rats. This was not in parallel, but it showed accelerated discovery. Okay, enough for a nature biotechnology. So do I shoot myself down? Oh, Alán, nature materials, nature biotechnology, did you move the needle? Well, this is a corollary of the story. This company continued working. Just last week or 2 weeks ago, they announced $255 million of funding because they already have a drug candidate for another kinase inhibitor generated with this technology. So somebody valued this company around $1 billion, okay? So this is happening. I talked to AstraZeneca people. AstraZeneca have some drugs that were generated this way in testing, right? Here is a Cell paper from MIT, Regina Barzilai. This is a paper from EPFL, both of them in antibiotics. So there are people already successfully generating drugs, okay? So let's go back to our problem, materials. For example, catalysis, CO2 catalysis, right? You guys know, we all wanna, convert CO2 in a polymer. We all want to fixate nitrogen. We all want to, etc., right? Catalyze industrial processes. Heterogeneous catalysts are some of the most important things that you can do, right? So my collaborator and friend, Yusong Jung from KAIST, took a generative adversarial network, another generative model. We trained it on a data set of the materials project, basically vanadium oxide. So we trained it on all the known vanadium oxides that were computed, basically, with VASP, okay? So after that, we have a sampler that samples and generates a PDF, right, of these vanadium oxides. And then if you see that P304 and or B508, and you look at energies above the convex hull that could be synthesizable, we find new phases, potential new phases of vanadium oxide, right? So that's pretty cool, right? Because in principle, you could calculate if they are good catalysts or bad catalysts, and in principle, you could actually make it happen. Same thing here, this paper, Nature Machine Intelligence, or another fancy journal. This is our state of the art in my lab. we did MOFs, these gas separation compounds in collaboration with Randy Snoor. This really was huge effort of postdoctoral worker in my lab, Shenpeng Yao. And we were able to predict very, very good MOFs, but we weren't able to make them yet. I mean, this just came out. And I noticed I had 10 minutes left because I'm trying to, enjoy my speed of this talk. So let me figure out what I'm going to tell you about. Let me skip machine learning. I'm going to do something. So I'm going to skip a lot of machine learning stuff. And I'm going to tell you about robots for the remainder of this talk, okay? Sorry about that. So I do want to follow the 40 minutes mandate so I can talk to you science one-on-one in questions, right? So I told you I had this crisis. It happened more or less at the same time Trump became president. So actually, I guess my midlife crisis, I was already tenured at Harvard, very happy there, but I didn't stand the authoritarian Trump. Looked around the world, moved to Canada, where I'm super happy. Canada, I would like to say, is you're taking a blender, Europe and the United States, you blend it, and what comes out is Toronto. Okay, so it's fantastic. So you should come visit me in Toronto, people in this room. So anyway, I'm super happy here. But one of the things I did is I started robotics, right? I mean, moving universities. So now I have a lab. I'll show you pictures of it and results. But anyway, the cool thing about it is that we started thinking about this idea of the materials acceleration platforms, right? Human intuition, orchestration, robotic platforms, databases, all of it together. So for the next 10 minutes, let me show you a little bit about it. So I banded with a bunch of cool people like Marty Burke, Lee Cronin, Bartosz, and Jason. And if you follow them in Twitter or know them, these people are pretty outspoken and like have a lot of creative ideas. And we created a DARPA project called Madness. And it's true madness because we really want to make this happen, right? So they have different robotics in their laboratories, but we're trying to then attack a materials class that there's very little known of. 2017, Chihaya Adachi publishes the first organic solid-state laser that lasts enough to be of interest. Same thing, but now imagine your cell phone emitting laser from the organic layer, okay? That would be super cool. But there's very few of them, so we said, why don't we design organic lasers? So now here comes the question of synthesis. How do I make organic molecules? I want to make them in a robot. So therefore, Marty work is extremely important in this work because I started becoming down the rabbit hole of a particular reaction called the Mida-Boronate-Suzuki coupling. Mida-Boronate protected Suzuki coupling, which is an iterative coupling scheme that is very similar to the iterative coupling schemes that nature uses to build peptides, saccharides, nucleotides, terpenes, etc. We are built by iterative coupling schemes. The reason we are so complex as biology systems is that we have these enzymes that are doing the same reaction over and over again on different substrates, assembling us, so to speak. As you know, that's the whole point of the central dogma of biology, right? So it's not surprising that you can reach 60 to 70% of all the natural products with about 3,000 fragments, according to my friend Marty Burke and his calculations, using a single reaction. Not surprisingly, this reaction couples carbon to carbon, right? So you have enough diversity in your blocks, you couple carbon to carbon, deprotect, couple, you can in principle build a big variety of organic molecules. Sorry, I'm getting a text message from a store. So you never know when you get a text message. But anyway, so you can see here all the different organic-like molecules, like these organic laser-like molecules that you can make with this technology, okay? So very conscious of time. Okay, now I only have 5 minutes left. Let me tell you a little bit of photophysics. What does it take to be an organic laser? Well, you want to look like a laser-like object, right? You want to have a very narrow line, very fast emission. You want to reduce the parasitic effects, right? Like excited state transition, intersystem crossing. Here, you want to reduce intersystem crossing. You want to reduce excited state absorption, separate the absorption and emission bands, etc. We know how to do that. We're physical chemists, so we do screening projects for that, okay? So we, for example, think about the following way. We explore chemical space in a forward manner, okay? In other words, we take 300 blocks, use the iterative coupling scheme I tell you about, filter it with the AI of Bartosz Rybałowski that tells us what are the reactions that cannot happen. So this Suzuki doesn't happen, right? So we have AI that tells us this Suzuki is not going to happen. This is the only Suzuki that happens. So we can prune that 100 million dimensional space and only computationally screen the molecules that actually the robot can make. So now we have a robot in my lab. We know which molecules it can make. We can do semi-empirical and DFT calculations, and then we can test it experimentally, right? So again, you can build a multi-dimensional parabola model compared to some of the models built by people in your institute. This is a very simple model. This is just a parabola model with pad integral calculations. You could do fancy things like MCTDH and things that you guys do, really, like you could continue and do fancier things. But remember, I am a screener, okay? So I screen with DFT, I build these models, they still Bavronicki result, I can put parabolas for the triplets, I can do more and more physics on it. But at the moment, I only have the singlet. I'm interested in the absorption and emission lines. And therefore, what I do then with the quantum chemistry, and for those of you that are quantum chemists, you can see my workflow here. I use DFT, Hessians in the ground and excited state, build my model, and then approximate it with gradients and ground state Hessians. And I can do XTV DFT, another German technology by Stefan Grimme, in about 15 minutes, right? So, really incredible, right? I mean, the fact that you can actually use this, and is it super accurate? Well, it's not super accurate. Is it good to screen? Yes. Is it good to screen what you would do with a robot? Okay, I'm gonna skip the laser model and show you the robot, right? Because I'm running out of time. So I'm very excited about this because I'm a theoretician that runs an organic chemistry lab connected to an analytical chemistry lab, connected to a physical chemistry lab in the same room. And this is, if you come to Toronto, next to the theoretical chemistry area. So it's super cool. We have theoretical chemistry, and then the room next door is this robotic lab. So you can see here the absorption and emission lines of a molecule that was synthesized, purified, and then sent to 3 lasers. Time resolved photoluminescence, absorption and emission in the CW, and also we have an excited state absorption laser back here that you cannot see, but it's covered over here. Okay, so that's kind of the setup in my lab. Just to show you that it works, here it is. I don't show you the structures, but here is a run. And this is perhaps my most proud slide of this presentation. This is the lab in Toronto run by a theoretician actually making these organic laser candidates. These colorful vials are actually these data points here. And these are real data points built in my lab. And we have these molecules that we measure the photoluminescence lifetime, the relative quantum yield, and some of the molecules here are better than Chihaya Adachi's lasers. Where are we? We made them, we sent them to, we're scaling them up right now. Turns out in Mexico. I was mentioned that I'm from Mexico, so my collaborators in Mexico are making big quantities of them. I'm gonna ship them to Japan to make the devices. So we're in the stage of demonstrating that my lab, robotics and all this AI stuff actually works, okay? So for the remaining like 3 minutes, let me tell you maybe another example, and then just ruminate about the future. Okay, so another area, I skipped the mathematics of it, but another area that I really like is Bayesian optimization. Okay, well, maybe I'll show you here, just this slide. My lab has developed algorithms called Phoenix, Griffin, Gemini, Olympus, Golem, Chimera. All these algorithms, what they do is they optimize in a low data regime chemical experiments. Okay, don't have time to discuss, but I'm going to show you a real-time experiment. We did 200 experiments with Merck, getting the data points for a catalysis problem, trying to maximize the E to C ratio of a real organic reaction. And our ChemOS software allowed us to optimize the yield of this reaction to 70%, which is more than what Merck was able to do in about 2 years with real humans. And you can see here the exploration in terms of temperatures, palladium ratios, etc., with our robot honing in into the ligand 30, and then particular reaction conditions that give you 70% enantiomeric yield. Okay, so we're very proud of these real case examples. So now let's talk about physical chemistry for the end. Okay, so we were here. This is where it never ends. So somebody that is amazing, Robert Police from Austria, a fantastic faculty candidate. If your institute is hiring, you have to send an offer to Robert Police yesterday, okay? Just incredible guy. He used to be with Peter Chen. He knows physical organic chemistry, AI, everything, okay? So Robert, Gabe Dos Passos Gomez, Cyril Lavin, and I just published in Matter the following. Let's go back to the original physical chemistry problem. Is it possible to have a triplet above the singlet in an organic molecule and also be bright? Turns out that a beautiful paper by Piotr Silva showed that you could have the triplet above the singlet, but he had a molecule that was dark. Okay, it was cool, right? We saw molecules with a triplet above the singlet, and we said, can we use our screening, computational screening tools and exploration to be able to find molecules that have an inverted singlet triplet gap called INVEST, okay, that are as bright as the OLEDs, right? And then emit light. And we just published this paper where we show a big set of molecules in this class. They look like this. And this is basically dynamic spin effects that actually destabilize the triplet with respect to the singlet, and then allow you to have the singlet up below the triplet and still have now 100% reverse system crossing, right? Because you're going downhill in energy. So we believe this is the 5th generation OLED, and we're very happy. So this tells you cannot abandon basic physical chemistry, right? You have to do everything, to do the basic physical chemistry, or also applied robotics or something if you really want to do something. So the future is going to be androids. Again, I told you like androids. So we're working in computer vision for 2-dimensional and 3-dimensional, I'm going to skip this, but also 3-dimensional computer vision for the robotic arms to do chemistry, okay? So in the interest of time, I'm skipping the details, but needless to say, we worked in the data set generation and also the AI models, of course, in collaboration with computer scientists to really build the robotic chemist of the future, which be a robot that will pick up a cup of coffee and mix it in an unsupervised environment. So this will take a while, but I believe this is going to be the robotic android of the future. And we're going to need it to actually do the experiments as fast as we need to hopefully try to be as good as the biologists and make a dent in the world. And with that, I'm going to end showing you a picture of my research group and acknowledging the work of all these brilliant people. It's without them, I wouldn't be able to do anything. I'm just the guy that goes around giving talks. And with that, I'm going to thank you and actually answer questions.